1959. The United States Air Force asked a team of physicists to calculate exactly how visible a nuclear explosion would be from Earth if you set it off on the moon. And one line, buried deep in this file, still doesn't have a clean explanation. The archive is open. Tonight's file is Project A119, the Air Force study on detonating a nuclear weapon on the moon and what it would actually prove. Page 1 doesn't hide the motive. 3 reasons, laid out cold: scientific, military, political. Read it.
The motivation for such a detonation is clearly threefold: scientific, military, and political. Obviously, however, specific positive effects would accrue to the nation first performing such a feat as a demonstration of advanced technological capability.
Translation: whoever nukes the moon first wins a propaganda war, but the same page admits the risk. Do it wrong, and the whole planet turns on you.
It is also certain that, unless the climate of world opinion were well prepared in advance, a considerable negative reaction could be stimulated.
So they didn't just plan the bomb, they planned the visibility of the bomb, how bright it needed to be, and from how far away, for the whole world to see America did it.
The brilliance of sodium cloud containing 1 kilogram of sodium and discharged 113,000 kilometers away from the Earth is equal to a 6th magnitude star. For detectability with naked eye at lunar distance, the amount of sodium required is, against sky background, 10 kgms, against dark side of the moon, 102 kgma, and against bright side of the moon, 105 kgm.
Numbers on a page are one thing, but the file also does the math in plain terms. How big a target has to be before you can just see it against the moon with nothing but your eyes?
Source of 1.3, 1013 candles visible. Source 1.3, 109 candles visible. 13 miles diameter, 0.4 mile diameter, 700-foot diameter.
A 700-foot sphere, painted white, sitting on the dark side of the moon, visible from Earth. No telescope. That's the bar they were calculating against, and a nuclear fireball was going to clear it by orders of magnitude. The file admits its own math has a flaw. The moon isn't a clean backdrop. It's craters, shadows, glare, all scrambled together. Page 15 spells out why that matters.
However, since the moon is not of uniform luminance, the results are not rigorous, ranging from unresolvable points to large irregular areas, and from bright spots to deep shadows, arranged in most irregular fashion. The moon represents a difficult background in which to search for a small area. Therefore, target intensities must be substantially greater than indicated by calculations assuming uniform background.
So every number before this one was the floor, not the ceiling. Whatever they detonated had to be brighter than the math said, just to survive the moon's own mess of light and shadow. Brightness was only half the file. The other half wasn't about seeing the blast at all. It was about listening to it. Page 45 pivots the whole study toward the moon's insides.
Seismic observations on the moon are of great potential interest from the viewpoint of fundamental theories of the development of the solar system and of the moon itself. It is not certain how much seismic energy will be coupled into the moon by an explosion near its surface. Hence, one may develop an argument that a large explosion would help ensure success of a first seismic experiment.
Read that twice. The bomb wasn't just a flashbulb for propaganda. It was a hammer tapping the moon to hear what it's made of. Page 1's political motive just picked up a scientific alibi. That seismic hammer only works if the moon is quiet enough to hear it ring. The file goes looking for exactly that kind of silence and finds a witness. Page 57.
Upon the moon, all such activity will be absent. Dr. Jack Oliver, a seismologist of the Lamont Geophysical Laboratory of Columbia University, New York City, has expressed the opinion to us that as a consequence, the moon would be expected to be seismically very quiet. The periods associated with the natural frequencies of an elastic sphere of the size of the moon are much larger than the periods of the usual seismic waves of interest in seismology or those associated with explosions.
No wind, no surf, no traffic, just rock, gravity, and whatever the bomb tells it. A quiet moon isn't a limitation here. It's the whole reason the experiment could work at all. 10,000 kilograms of sodium, just to be seen against a bright moon. That's the file's obsession. Visibility. But there's a quieter chapter here about what the moon does when nobody's watching. So they ran the numbers both ways. Light moon, dark moon. The gap between the two is the whole reason 10,000 kilograms of sodium sounded reasonable to somebody. Zoom out, and the motive gets bigger than acoustics. Page 10 lays out why anyone would even consider putting a nuclear weapon on the moon in the first place. That 1,000-fold gap between a bright moon and a dark one wasn't theoretical. Page 20 puts actual numbers on it, and the difference in required brightness is staggering.
Light moon, B0 yields 0.25 candles cm2. Dark moon, B0 yields 0.025 candles cm2. Source of 1.3 at 1013 candles visible. Source 1.3, 209 candles visible.
10,000 times more light needed just because the background changed. That's the arithmetic that eventually lands on sodium. Page 28 explains why that particular element won the argument.
The motivation for such a detonation is clearly threefold: scientific, military, and political. The scientific information which might be obtained from such detonations is one of the major subjects of inquiry of the present work. On the other hand, it is quite clear that certain military objectives would be served, since information would be supplied concerning the environment of space, concerning detection of nuclear device testing in space, and concerning the capability of nuclear weapons for space warfare.
Scientific curiosity wrapped around a demonstration of power. The file admits that much before it ever gets to seismographs. Quiet enough that a single nuclear blast becomes a probe into the moon's actual insides. They even ran the math against real underground shots: Rainier, Logan, Blanca.
The coupling of the energy of the detonation to the Earth was such that the resulting seismic signal for the Rainier shot was equivalent to that observed from an earthquake with a scale value of 4.6 on the Gutenberg Richter scale.
A kiloton bomb, detectable 300 to 400 miles out. A megaton bomb, the file says it plainly.
The kiloton bomb would be detectable at a distance of 300, 400 miles, while the megaton bomb would be detectable anywhere on the moon.
Anywhere on the moon, one bomb, one instrument, the entire surface. That's the ambition. Now the file turns to what a bomb like that leaves behind. The physicists model a 1 megaton burst above the lunar surface. Half the fission products, they assume, just drift off into space. The other half stays.
Detonation of a 1 megaton bomb above the surface of the moon with the following assumptions. 1. The fission yield is 500 kilotons. 2. 1/2 of the fission products are retained by the moon and 1/2 are lost in outer space. 3. Uniform spreading of the fission products occurs over the entire lunar surface.
They call this a conservative estimate, meaning the real fallout could be worse, and they knew it. A month or two later, they claim, the radiation drops to background levels. Convenient math for a plan that never left the drawing board, yet. A demonstration, not an experiment. A flex, aimed at the sky for everyone on Earth to see. Which raises the next problem. If the whole point is being seen, someone has to prove it happened. Translation: the moon won't hold still and light up on cue. Whatever they detonate has to outshine chaos itself, not just the dark. 13 miles wide against a bright moon, or 700 feet against a dark one. That's the price of visibility, a fireball the size of a small city, or timing the shot for shadow. Either way, nothing about this was ever subtle. But radiation wasn't the only worry buried in this file. There's a science question nobody in 1959 could answer. Does the moon have a molten iron core? And the answer they propose is strange. Straight from the folder.
If a field of the order of the Earth's 0.11 Gauss is detected, this will be taken as strong a priori evidence for the existence of a liquid iron core.
So the bomb isn't just a weapon in this file, it's a magnetometer, a crude, radioactive way of asking what's inside a rock 240,000 miles away. And what they don't know yet is almost more interesting than what they do.
There is direct seismological evidence for the existence of a liquid terrestrial core, but of course no present lunar seismological information, and there exist theories for the origin of planetary magnetic fields which do not involve liquid cores.
That's the trade. Against a sunlit moon, you'd need a source blazing at 13 trillion candles, or a sphere 13 miles wide. Against the dark side, a 700-foot sphere would do, which is, quietly, an argument for detonating on the far side, in shadow, not the near side everyone pictures. They're guessing, educated guessing, with slide rules and Cold War funding, but guessing. What you're about to hear stayed classified for decades. Listen.
If such a biological contamination of the moon occurred, it would represent an unparalleled scientific disaster, eliminating several possibly very fruitful approaches to such problems as the early history of the solar system, the chemical composition of matter in the remote past, the origin of life on Earth, and the possibility of extraterrestrial, all life.
Read that again. The same file, planning a nuclear strike on the moon, is warning that the moon might already carry evidence of alien biology, and that America could destroy it by accident. That's the sentence nobody in this file ever resolves. The bomb they're planning could erase the very thing they claim to be searching for, and there's a committee for that fear too. Real names.
M. Calvin, U of Calif, Berkeley, Chemistry, Chairman, J. R. Platt, U of Chicago, Physics, CMDR, M. Ross, ONR, USN, C. Sagan, ARF, Yerkes, Astronomy, G. Stent, U of Calif, Berkeley, Virology, R. Vishniak, Harvard, Microbiology, H. F. Weaver, U of Calif, Berkeley, Astronomy.
Look at that list again. Berkeley, Chicago, Harvard, the Navy, and one name in the astronomy column that would become the most famous science communicator on Earth. Carl Sagan. Years before Cosmos, years before he was a household name, sitting on a committee arguing that we might contaminate or destroy evidence of life beyond Earth. And their conclusion on the contamination risk tried to sound reassuring. It comes from a committee report near the end of the file, one paragraph doing a lot of heavy lifting, straight from the folder.
CTEX feels that the likelihood of any biological contamination of the moon is very small, since the possibility of reproduction of a deposited terrestrial microorganism is taken to be negligible.
Negligible, that's the word they land on. For a decision that would put a nuclear weapon on a body they admit they don't understand. No detonation ever happened. The file was shelved, then buried, then declassified decades later. What's left is 208 pages of a country deciding, seriously, whether to detonate a nuclear weapon on the moon to win a propaganda war it was already losing to Sputnik. It never happened, but the paperwork did. Every file we read tonight is linked below. Don't take our word for it. Read them yourself, and if you want the next file on your desk, subscribe. New files every Tuesday and Friday.